Today on How It's Made. Laminate, a report that probes beneath the surface. Frozen treats will bring you the cold, hard facts. Children's building blocks, from automated production to manual construction. And detergents will come clean and reveal the behind-the-scenes secrets. Laminate is a thin decorative surface layer that's usually glued onto a particle board base to create a countertop. Laminate is by far the most affordable countertop material on the market. It comes in endless choices of colors and patterns, from solids to simulated wood or granite. They also use laminate for kitchen cabinets, furniture, and laboratory surfaces. And they manufacture fast food restaurant seating, among other things, out of a thicker, solid form of the material called compact laminate. The back of a laminate sheet is made of a type of craft paper that can be saturated without becoming soggy and tearing. A treater drenches it with resin containing phenol, a compound derived from benzene. The resin doesn't merely coat the paper, it absorbs right through. The paper then enters a drying oven. The hot air cures the resin in a matter of seconds. Now they can wind the paper into a roll. The top of the laminate is called the decorative layer. It's a sheet of paper in either a printed design or a solid color. Solid color papers go through a treater that impregnates them with a more durable melamine resin. Durability is essential because the decorative layer must withstand wear and tear. Two big rollers wring out the excess resin, then the saturated paper goes through a drying oven. With the resin now cured, a cutter slices the paper into sheets. Before resin treatment, the paper was flexible and easy to tear. Now it's stiff and brittle. Bend it, and it snaps like a potato chip. While the rolls of saturated craft paper get cut into sheets, workers prepare the other style of decorative layers, those with printed designs such as simulated wood grains and granite. The treatment process for these papers is quite different than that for the solid color papers. Workers start by cutting them into sheets the same length as the craft paper sheets. These papers don't go into a treater to be saturated with resin. Instead, workers stack them, placing an overlay on each one. An overlay is a transparent sheet of paper that's saturated with melamine resin. Workers stack the solid color sheets in the same pile, but those don't need overlays because they've already been resin saturated. Now the stack goes to the press room. There, workers put saturated craft paper under each decorative layer. On top of each decorative layer, they lay a textured plate. This will prevent the finished laminates from sticking together. Everything now goes into a press. The intense heat and pressure compress the layers. The overlays bond to the printed papers, and the saturated craft paper bonds to each decorative layer, creating laminate sheets. The textured plates between each set, meanwhile, imprint their pattern onto the heat-softened resin, texturing the laminate surface. The laminates come out of the press fully cured. On the finishing line, machines trim off any excess paper on the edges and sand the back of the sheets. This helps the laminate adhere better when glued to particle board or another type of substrate. To produce compact laminates, workers compile a thick stack of black saturated craft papers and sandwich it between two decorative layers. The press melts and bonds all the sheets into a solid unit. Alternating colors produces a striped edge. Compact laminates are so thick they're entirely self-supporting, so unlike laminate sheets, they don't need to be applied to a substrate. On a sweltering summer day, a frozen treat sure hits the spot. Eating a fruit bar, fudge bar, or ice cream bar, though, requires a certain strategy. You have to hold the treat by the stick, lean slightly forward to dodge the drips, then lick like crazy before it melts off the stick and lands at your feet. The outer shell of these cream pops starts with a transparent base made of water, liquid sugar, corn syrup, citric acid, and a stabilizer. It travels to 3 separate compartment vats, each of which mixes in a different coloring and flavoring. This company produces 3 flavors of cream pops: strawberry, orange, and blue raspberry. Each compartment vat pumps its flavor to a machine called the filling hopper. The hopper injects the liquid into row upon row of 60 milliliter pop-shaped molds. This production line has 340 molds in continuous motion. The molds descend into a tank of brine, water chilled to minus 35 degrees Celsius, mixed with calcium. Calcium works like antifreeze, keeping the water liquid despite the below freezing temperature. As the molds travel through the ice-cold brine, the liquid freezes from the outside inward, creating a shell that will encase the Pop's ice cream filling. Once the shell is 3 millimeters thick, a machine called a suction evacuator removes the unfrozen liquid and feeds it back to the filling hopper to be re-injected at the start of the line. The shells are empty now and ready for filling. The ice cream filling is made of various milk products blended with liquid cane sugar, corn syrup, stabilizers, and emulsifiers to puff up the consistency. The factory pasteurizes the mixture, heating it for 35 seconds at 80 degrees Celsius, then freezing it. Then it homogenizes the filling, skimming off the milk fat that rises to the surface. The shells are still floating in brine as they reach the filling station. The machine shoots in the ice cream, overfilling the shell a bit to create a 1 centimeter cap. The ice cream begins to harden in the cold brine. Once it reaches a semi-frozen state, a machine appropriately called the stick inserter pops a wooden stick into each mold. Now the molds leave the brine and enter a tank of warm water, 24 degrees Celsius, hot enough to detach the cream pops from the molds without melting them in the process. From initial injection to final extraction, it's been 7 minutes. The machine dips the cream pops in cold water to produce a protective coating of ice. This will keep the surface from sticking to the wrapper. It will also lengthen the product's shelf life. The machine deposits the cream pops into a continuous stream of paper wrapping. Heating elements seal the wrapper on top and between pops. Then a slicer cuts them apart. The empty molds go through an automatic wash and rinse cycle on their way back to the start of the line. These molds are for making chocolate fudge bars. The production process is the same, except that the shell is fudge flavored, made from milk solids and chocolate powder. And instead of ice cream in the center, there's chewy chocolate syrup. The factory stamps the packaging for all its frozen treats with the production date and other information. These frozen treats have a 1-year shelf life in the freezer, provided you maintain the temperature at an ideal minus 25 degrees Celsius. Few toys are as timeless as interlocking building blocks. Children can stick them together, pull them apart, and rearrange them endlessly. From large-size blocks for babies to intricate kits for older kids, building blocks stimulate creativity and improve manual dexterity. This company makes plastic building blocks. Depending on the type of block, it uses either polypropylene, high-density polyethylene, or high-impact polystyrene. These plastics arrive at the factory in pellets. Because they're naturally transparent, the first step is to color them. The pellets go into a mixer along with pigment beads made of powdered pigment in a type of plastic that's compatible with the pellets. The pigment beads make up just 2% of the weight, but that's enough to color the plastic a deep hue. The mixer feeds a plastic injection machine. It heats the pellets to 204 degrees Celsius, melting them in a matter of seconds. The machine then injects the molten plastic into molds. A system of hoses cools the molds with cold water, instantly hardening the plastic. When the machine opens, ejectors thrust the blocks to a conveyor belt below. For these blocks, the entire cycle from start to finish takes just 14 seconds. The length of the cycle varies with the size of the block. This large school bus, for example, requires more plastic, so injection molding takes 22 seconds. The wheels for the bus take 20 seconds. Packaging time, each type of block is loaded into a separate vibrating bowl. The shaking separates the pieces, enabling them to pass by an optical counter one by one. This automated counting equipment can tally up to 16 different types of blocks at a time. It can be programmed to assemble a kit consisting of specific quantities of certain blocks. Once each kit is counted, it drops into a bucket. The factory also makes the buckets by plastic injection molding, and it even incorporates the labeling right into that process. Here's how it all works. A robot takes 2 labels, one for the front of the bucket and one for the back. It passes a static generator that charges them with static electricity. Then it loads the 2 labels into the mold. The static cling holds them in a flat position while the machine injects the plastic and molds the bucket. The hot plastic melts the labels on contact, melding them into the finished bucket. The result? Labels that can't be peeled off. The factory produces large blocks from polypropylene or high-density polyethylene, which are flexible plastics. This makes the blocks easier for young children to use. Small blocks are made of high-impact polystyrene, a plastic that can be molded with great precision into tight-fitting blocks designed for older children. Just walk down the aisle of your local supermarket and you'll see shelves upon shelves of soaps and detergents. With so many versions of each product to choose from extra strength to antibacterial to lemon fresh scent, consumers aren't the only ones cleaning up. The craft of soap making began in Europe around 700 AD. But soap remained a luxury item for another 1,000 years. That's when a French scientist discovered how to make inexpensive lye using table salt. People also made soap at home by boiling wood ashes with animal fats. By the 1900s, the growing soap industry finally found ways to make mild and fragrant products. And in 1916, a German scientist invented the first synthetic detergent. This company produces mostly industrial-use detergents, liquid and powdered. It uses salt as a filler in the powdered ones. Fillers add volume, making a product less concentrated. This will be a powdered detergent for cleaning and degreasing cement floors. They add colorant, then surfactant, a substance that creates foam, the vehicle for lifting away dirt. Now they pour in pine oil, a disinfecting agent that also adds fragrance. Now, the cleaning agent, the chemical sodium tripolyphosphate. It's essential to mix all the ingredients thoroughly. This ensures the chemicals are evenly distributed throughout the cleaner. The last ingredient is a chemical called sodium metasilicate. It boosts the mixture's alkaline level. This particular cleaner needs high alkalinity to be effective. The factory packages its powdered cleaners, such as this laundry soap, in large plastic buckets. Automated equipment weighs, then pours in the appropriate amount, capping the container tightly to prevent leaks. The filler in liquid cleaning products is water. To produce liquid hand soap, they first add citric acid. This creates the mild acidity needed to get the most out of the surfactants. This soap contains 3 different types of surfactants, a specific formulation designed by the company chemists to optimize the soap's cleaning power. To give the soap a pearl luster, the company uses this secret recipe of chemicals. The factory makes most of its liquid soap from this same base mixture. The colors and fragrances vary. For coloring, it uses powdered pigments. It dissolves them in hot water, then pours them in. This batch of soap will be pink. They pour in a rose-scented fragrance, then add a preservative to prevent the proliferation of bacteria should the soap be exposed to a substandard environment. Finally, they adjust the viscosity by adding a powdered thickener. If liquid soap is runny, it'll leak out of the dispenser. After 15 minutes of mixing, the soap is ready, and the lab analyzes a sample, assessing its physical and chemical properties. When the batch gets the okay, it proceeds to the packaging machine. This soap is going into dispenser bags made of plastic film. The machine first inserts a valve. It heat seals the film, forming the bottom of the bag. Then it injects 800 milliliters of soap. Next, it simultaneously heat seals the top of the bag and the bottom of the next one. It cuts them apart, releasing the finished bag to a conveyor belt below. After checking for leaks, workers insert a spout that controls output from the valve. This ensures the dispenser will release only a few grams of soap per push. Elsewhere in the factory, an automated machine called the pressure filler pumps dishwashing liquid into plastic bottles. An overflow and weight control device ensures the right fill level. The next machine applies a twist cap with a pull-out spout. Then it's off to labeling. Those bags of liquid hand soap, meanwhile, went into special boxes that are designed to slip right into the soap dispenser. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net. The How It's Made crew vehicle is courtesy of Subaru Canada.